In the next few sessions, we'll be looking at the nature of some standard sequences. So here we will look at the nature of standard sequence 1 plus 1 by n to the power of n. So we have a n is equal to 1 plus 1 by n to the power of n. Let's expand it using the binomial theorem. So we have a sub n is equal to 1 plus n by 1 factorial times 1 by n plus n times n minus 1 by 2 factorial times 1 by n square and so on. Now this is purely based on the binomial theorem. This is called the binomial expansion. Now let's simplify this. We get 1 plus, now n cancels out. So we have 1. So we have 1 plus 1, 2 plus. Now here, let's take n out. So what do we have? We have n square times 1 minus 1 by n. N square cancel out. So we are left with 1 minus 1 by n by 2 factorial. Plus, similarly, we keep simplifying this to arrive at 1 minus 1 by n times 1 minus 2 by n divided by 3 factorial. And so on. Now, there's a short way in which we can represent this using the product notation. Just like we have the sigma as the summation notation, this is the product notation. So product of 1 minus k by n, where k goes from 1 to n minus 1, divided by n factorial. So this is a sub n. Now, just to conserve some space, I will remove these two steps and bring this up. Note that k by n is a proper fraction, since k goes from 1 to n minus 1. Hence, 1 minus k by n is positive for all such k and n. Now, let's look at this, a sub n plus 1. So basically, we substitute all the n's here with n plus 1. We have 2 plus 1 minus 1 by n plus 1 by 2 factorial plus 1 minus 1 by n plus 1 times 1 minus 2 by n plus 1 by 3 factorial and so on. And here we end up with an additional term. The product of 1 minus k by n plus 1, where k goes from 1 to n plus 1 minus 1. So n, the whole thing divided by n plus 1 factorial. This is the nth term and this is the n plus 1th term of the sequence. Note that the final term in a sub n plus 1 has no corresponding term in a sub n. This is the n plus 1th term. Now comparing the two expansions, since n plus 1 is greater than n, implies 1 minus k by n plus 1 is greater than 1 minus k by n for all k with k between 1 and n minus 1. So hence, each term starting from the non-constant term onward of a sub n plus 1 is greater than the corresponding term of a sub n. So ignore the 2's. They are equal, constants, whereas the rest have n's. So each of these terms is greater than this. So therefore, a sub n plus 1 is greater than a sub n for all n in natural numbers, which implies that the sequence a sub n is a monotonic increasing sequence. Now, here comes the tricky part. Here in this sequence, these are all proper fractions, right? Since we said 1 minus k by n is positive for all such k and n, and we said that k by n is a proper fraction, That means 1 minus k by n is less than 1. So if we substitute these with ones, a sub n will become less than or equal to this sum, where the numerators contain 1 instead of 1 minus k by n. Short reasoning is because this is between 0 and 1. Let's again, substitute this with another one where we can say that a sub n is less than that series. So let's do this substitution. A sub n is less than 1 plus 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube and so on up to 1 by 2 to the power of n minus 1. Now, how can we do this? Because we know, or we can see that 1 is equal to 1, 1 is equal to 1. 1 by 2 factorial is nothing but 1 by 2. So 1 by 2 is equal to 1 by 2. So first three terms are the same. Now let's look at the next one. 1 by 3 factorial is 1 by 6. And 1 by 2 square is 1 by 4. 1 by 6 is less than 1 by 4. Similarly, 1 by 4 factorial, that is 1 by 24, is less than 1 by 2 cube, that is 1 by 8. And so on up to the last term. 1 by n factorial is less than 1 by 2 to the power of n minus 1. So that means what? Since this is less than this, a sub n cannot be equal to this. So it is less than this. So the expression in the square brackets is a geometric series. And we know the formula for the sum of a geometric progression, which is a times 1 minus r to the power of n by 1 minus r. So now let's apply this formula. We have a sub n is less than 1 plus a. A is 1. So there's no point in multiplying with anything. So we ignore this one. Then we have 1 minus r to the power of n. So here r is the common ratio, that is 1 by 2 to the power of n divided by 1 minus r. So 1 minus 1 by 2. Now let's just keep simplifying this. So we have 2 to the power of n minus 1 by 2 to the power of n divided by 2 minus 1 by 2, which gives us 1 plus 2 to the power of n minus 1 by 2 to the power of n by 1 by 2. 1 plus this 2 goes up. So 2 times 2 to the power of n minus 1 by 2 to the power of n. 1 plus distribute 2. So 2 to the power of n plus 1 minus 2 by 2 to the power of n. Now split this. We get 1 plus 2 to the power of n plus 1 by 2 to the power of n minus 2 by 2 to the power of n, which gives us, here if we take 2 to the power of n up, we get 2 to the power of n plus 1 minus n. So we are left with 2. That 2 plus 1 is 3 minus, we get, if we take 2 down, we get minus 1 by 2 to the power of n minus 1. And since minus 1 by 2 to the power of n minus 1 goes to 0 as n goes to infinity, we have a sub n is less than 3 for all n. So which means 3 is the upper bound because all the terms of the sequence are less than 3. Now the first term is 2, a sub 1 is 2, and we have already shown that a sub n is a monotonic increasing sequence. That means a sub n is greater than or equal to 2 for all n. So therefore, 2 is the greatest lower bound or infimum. Now, since we have 2 is less than or equal to a sub n, which is in turn less than 3, we can say the sequence a sub n is bounded above and below. Now that we have arrived at this, let's look at some specific powers of 1 plus 1 by n. So limit as n goes to infinity of 1 plus 1 by n to the power of 1 is equal to 1. Pretty straightforward. It's a trivial case. Why? Because as n goes to infinity, 1 by n goes to 0. That means 1 to the power of 1, which is equal to 1. Now, limit as n goes to infinity of 1 plus 1 by n to the power of 1 by n. This is also equal to 1. We can't mathematically be right if we say that 1 by n goes to 0. This 1 by n goes to 0, which means we have 1 to the power of 0. Now, 1 to the power of 0 is indeterminate. So the right way of thinking is limit as n goes to infinity of, we take the e to the power of log of this. Now e and natural log are inverses of each other. So it doesn't change the value of this. So e to the power of natural log of 1 plus 1 by n to the power of 1 by n, which means 1 by n can be brought down now because of the natural log. So we have limit as n goes to infinity of e to the power of 1 by n times natural log of 1 plus 1 by n. And now we take the limit. So what happens? 1 by n goes to 0. This goes to 0. We have 1 plus 0, 1. Natural log of 1 is 0. 0 times 0 is 0, which means e to the power of 0. And e to the power of 0 is 1. Let's look at the specific case that we have in front of us. That is 1 plus 1 by n to the power of n. But before that, why is this sequence important? Because Euler's number E is defined as the limit as n goes to infinity of 1 plus 1 by n to the power of n. And E is approximately equal to this. But remember, this is an irrational number. So it keeps on going. So since E is defined as a limit as n goes to infinity of 1 plus 1 by n to the power of n equal to E. And which means the least upper bound or supremum is E. So here 3 was our upper bound, but E is the least upper bound. Finally, we have limit as n goes to infinity of 1 plus 1 by n to the power of n plus 1 is equal to E. Why? This can be thought of in two different ways. Limit as n goes to infinity of 1 plus 1 by n to the power of n times limit as n goes to infinity of 1 plus 1 by n. The power of n we already know is E. And to the power of 1, it will be 1. So E times 1 is E. That is one way of thinking. A shortcut way is just to realize that as n goes to infinity, naturally n plus 1 also goes to infinity. So which means it is equal to E. The importance of the sequence lies in the fact that it naturally arises in the computation of compound interest. As the number of compounding periods increases, the expression approaches E, leading to the concept of continuous compounding. This limit also forms the basis of exponential growth and decay models in biology, finance, heat conduction in materials, geology, etc. This is very, very important. And we have just explored its nature in detail in terms of it being monotonically increasing sequence, in terms of its lower bounds, upper bounds, greatest lower bound, least upper bound, and its limits for various powers. If you found this session helpful, please do Like, share, and subscribe. Comments, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.